Yeah, I know. It's not doing anything because it's not powered up. This is the latest iteration of our illumination controller. This is the rotary encoder which generates digital signals that gets interpreted by the electronics on this red circuit board that turn into an amount of current that gets sent to this driver board. And this driver board is connected to LEDs, which illuminate based on the intensity that we set with this. It's a pretty simple device, but we have created this from scratch. And if you've been following along on the journey, you've been watching it. If not, I'll make sure to include a link in the description so you can see everything we've done up until this point to create all of this wonderful circuitry. But as you might imagine, the circuitry, which is on these printed circuit boards, is a little naked. So we need to create an enclosure, a 3D printed enclosure to go around this. Now, this is not the first time we've created a 3D printed enclosure. We've actually done this a few episodes ago for a previous iteration of this design. This time, of course, the design is different, so it's going to require a different enclosure, but also we're going to use some different tools. We're actually going to use OpenSCAD, whereas last time we used FreeCAD. So we'll get into the details about that in a bit. But first, I want to talk about what we're actually going to start creating. If we flip the controller board over, you'll see there's actually room here for 6 of these driver modules. Here's one right here, another one can go there, another one over here, and 3 more on the opposite side. And the way this driver module is connected, it's actually just plugged in using a set of pins. I know it's tough to see on the camera, but these 2 here are the power pins, and if I roll it that way, and these ones over here are the 6 data pins. You might notice though, this thing is a little bit flimsy. So one of the things we're going to need to do is 3D print a support that'll serve as a conduit for this thermal connector in the middle, so it connects to the controller board on the other side. These other 2 connections here, those are the connections that will send the current right out to the LED. These connections have been designed for these spade connectors. These spade connectors will connect to the board using a screw, washer, and nut combination. So we have a washer on the top here. I know it's tough to see, but it will slide into the spade connector like so, and the hex nut at the bottom will anchor it to the board. The hex nut will be positioned like so, but there needs to be something in place to prevent the hex nut from spinning when screwing it in on the other side. This thermal conduit's also going to use a screw, which is going to attach to the bottom of this controller board using the same hex nut. So we also have to devise a way for that hex nut at the bottom of the controller board to not spin when being screwed in from the top. So this part that we're going to be designing is going to have at least 3 hex nuts, one for the positive, one for the negative, and one for the thermal. It's going to have a spacer to make sure that this thing doesn't jiggle around. It's going to include a rim to fit snugly around this driver. And this entire part is going to be pretty small, so it's going to have some intricate details. Let's get started. If you haven't used OpenSCAD before, here's a website where you can go get it. There's a download link on the main page, but it appears as though this one is fairly dated. But if you go over to the downloads link and scroll down a bit, there it is, you'll find this thing called development snapshots. These ones are a lot more recent, and this is the one we're using right now. The other thing you're going to want to do is to open up the cheat sheet on your main screen. You'll find it on the main page right over here. Click that. This thing is amazing. It is going to be so useful for us as we get into this. Once you fire up OpenSCAD, it looks like this. Here's your window where you can actually look at the 3D model. At the bottom is, well, some details, errors will show up over here. So this is going to be helpful to find out what's going wrong with your model. On the right, we have this thing called a customizer. We'll get into that a little bit later. And on the left is your code window. Now you can totally use this editor to enter in your code, but I really wasn't fond of it, so I went and got something else. This one, Visual Studio Code. It's a Microsoft application and freely available, so easy to get. If you're going to use Visual Studio Code, there's an essential step you really need to do to make life easier. This extension over here is going to be super helpful for our work. When you get started with Visual Studio Code, it actually goes through a little bit of a wizard that asks you what kind of things you're going to be using. Try to find this extension. If you've already installed Visual Studio Code, open this extensions tab over here, and in the search box, search for this extension. Once you've done that, we're ready to get started. Let's start with our first line of code. Let's start with defining a parameter for the radius of these hex nuts. Now, if you're following along and using your own nuts, they're probably not the same size as mine. So you might want to get yourself a micrometer, which is fantastic for measuring these tiny little parts. The radius of the hex nuts that we're using measured in at 3.5 millimeters. Now, if you're used to coding, this looks like defining a variable, and in a sense we kind of are, but in OpenSCAD's variables behave a little bit differently. See, when we did this before in Python, Python is a sequential language. Everything is kind of done one row at a time, so there's this concept of before and after. Whereas in OpenSCAD, it's not quite the same. There is no concept of before and after, so this is more or less like a parameter rather than a variable. In other words, if you try and change this variable later on in your code, you'll find that OpenSCAD doesn't recognize the change, and it will simply use the new value for all of the different times that you've used that variable. So this is a little bit of a shift in thinking, and you're gonna have to get used to it if you want to use OpenSCAD. So instead of calling it a variable, we're gonna call it a parameter. Now we're gonna use that parameter in an instruction that says circle parentheses hex sync radius. If we pop open the cheat sheet, you'll find circle in the 2D section. Here it is right there. You'll see that all it needs as a parameter is radius or diameter. If you choose to use diameter, then you have to put the d equals. Since we're defining the radius, we're just going to leave it and just put the value of that parameter, or I guess more accurately, include the parameter in the parentheses of circle, like we did. Every instruction needs to end with the semicolon. You're going to see as the code starts getting more complex that some lines don't have semicolons and some do. You'll understand why that is as we start getting into it. And when you render it, there it is. There's our little circle. Now, a couple of things you'll notice about this circle. One, that circle was created at the origin, meaning the intersection of the X, Y, and Z axes. When any sort of object is created, it's always created at the origin. You'll also see that the circle was created face down on the XY plane. This is also one of the rules of OpenSCAD. Every 2D element is always created flat on the XY plane. And finally, you notice that the circle appears to have a thickness, even though we didn't really give it a thickness. So speaking of that, let's give it some thickness. We're going to add another parameter called hex sync intensity, and that intensity is the thickness of this hex net, which I've measured at 2.3 millimeters. To give this circle some thickness, we use a command called linear extrude. Jumping back into our cheat sheet, you'll find it right here under the 3D box. And it shows here that the linear extrude accepts a few different parameters. The only value that's required here is height. And so that's the only parameter we're going to give it, the intensity of this hex net. And when we render that, look at this. Now it's got a proper thickness. Every 2D object that is extruded by the linear extrude command always extrudes in the positive Z direction, and the resulting 3D object will always sit on the XY plane. Now it's nice that this solid was created at the origin, but that's not really where it's supposed to be. It needs to be translated to its rightful place. In order to figure out where that rightful place is, let's open up the original design drawings. This is the printed circuit board layout that we created for that driver. If you want to see the video where we made this, take a look. So let's examine the cathode connection over here. This is where that hex nut is going to fit around. If I open up the properties, you'll see that the center of this terminal was positioned at 5 millimeters X and 5 millimeters Y. And going back to our physical one, the center of this terminal is 5 millimeters to the right and 5 millimeters up. And here's the command to translate this linear extruded circle to 5 by 5. Naturally, you'll also find it on the cheat sheet right under here under transformations. Note, translate actually includes a 3-dimensional vector, x, y, z, but it will accept a 2-dimensional vector like we've put in over here. And when we render that, lo and behold, our solid moves 5 millimeters to the right and 5 millimeters up. But remember, there were 2 terminals. That means we're going to need 2 hex pockets. Going back to the PCB design, there's the other terminal right over here. I could find the location of this terminal too by opening up its properties. See, this one's located at 23.4 millimeters in the x-axis and 5 millimeters in the y-axis. Of course, going back to our physical board, that's this one right over here. So to create another solid in our code, we simply need to add another instruction. We're using the same circle hex sync radius instruction, which is linearly extruded by the same intensity, but the translate is different. This one is actually translated to the 23.4 in the x direction and 5.0 in the y direction. Rendering that, oh, now we got 2, all positioned in the proper place. Notice in the code, we've defined parameters for these values over here, but the translate vector does not have a parameter. We could create parameters for each x and y offset for the translate vector, but we can also create a parameter for the entire vector, like this. Here's a parameter, we'll call it vTerminal0 and put the appropriate xy measures in there. And here's the other parameter, vTerminal1, we'll put the appropriate measures in there. Then I'm going to change this hard-coded value over here to reference the new parameter. And the same for this one. Notice how I prefix these parameters with a small v. I'm going to want to include some comments to describe what we're doing over here. So right at the top, I'm going to insert a comment that highlights a v refers to a vector, and it should, in most cases, have an xyz coordinate. You notice how the vectors are encapsulated in these square brackets. That defines a list of items. In this case, we're defining a vector with an x and y component. So it's a list of two values, x and y. We've seen in this cheat sheet that we could add a third value in there to make it x, y, and z. But those square brackets don't have to mean just vectors. They can mean any arbitrary list of elements. The other parameters in the code define the radius and intensity of these pseudo-cylindrical objects like these hex nuts. Now we're going to see a few more cylindrical objects in our code like these screws and washers. So there's a way to kind of package up these two parameters that describe the same thing by using the same concept of a list. But if we keep our naming, standards well defined, then it will be easy to remember as we go forward. So I've come up with this idea of a proportion. Let's combine those two values, the radius and intensity, into what we're going to call a proportion. Our proportion object is going to be prefixed with a P that defines the hex sync. And you can see the square brackets here. I've put the radius first and the intensity second. Once we have that parameter set up, I can remove these other two. So I'll take our new parameter and insert it into these values. Now it's not going to work like this because the linear extrude and the circle instruction expect a single value to describe that height, but we're giving it a list of two values. So we have to describe which item in that list is the one that needs to be sent to those two instructions. We need to access the intensity of this proportion for the linear extrude, which is the second value. And since lists in OpenSCAD are 0 indexed, that means it's value number 1. So we can do something like this, which means the radius is going to be value 0. Now this will work just fine, but OpenSCAD has another way to access the first 3 items in any list that you give it. You can use the .x, .y, and .z, suffixes to access the first 3 items. If you wanted to access the 4th and beyond item, you must use the square brackets with a number. But since our proportion only has 2 items, the radius and intensity, we could use the x and y to access either one of those respectively. So we'll change this to .y and this to .x. And we're gonna wanna add a comment to explain that peculiarity. I wish there was a way to kind of custom define those suffixes so I can say .r for radius or .I for intensity, but I couldn't figure out a way to do that. Maybe there's a way, but I'm not one of those pro programmers. So if you know how, please let me know. Now this is a neat little piece of code that we've written here, and you've probably already noticed a few particular things about it, specifically the order of which I've included these instructions. Now in both of our commands, the circle bit is at the end and the translate bit is at the front. So the way this should be interpreted is go to the end first. We're creating a circle and then work your way back up that branch. So we create the circle, then we linearly extrude that circle to make it into a solid, and then we translate that circle to where it needs to be. Now we could theoretically replace the translate and linear extrude instructions in that line, and there would be no change because what we're doing is we're creating a circle, translating it to where it needs to be, and then linearly extruding it, which would be fine. But if we put the circle ahead of any of those 2 items, this thing would fail because you can't linearly extrude nothing, right? The order of these instructions in that line is extremely important, and you'll also be able to identify some efficiencies if you pay attention to how these objects or how these modifications are performed on the various instructions. So let's try it. I'll take this linear extrude and put this in the front of both lines. And when we render it, there's no change. This works just fine. Now by doing that, we've identified our first efficiency that we can apply. These 2 linear extrude commands are identical, so we can actually factor it out and have one modification apply to both circles. By placing both of those translate circle instructions inside a scope that is surrounded by the linear extrude function. There's going to be plenty of efficiencies like this that you're going to find that are going to make our code shorter and more easier to read. Now these are wonderful little circles, but they don't really look like hexagons. So we're going to have to adjust the number of sides that these solids have. Lucky for us in OpenSCAD, there's a really easy way to do that. Going back to our cheat sheet, there's a special variable here called $FN, which identifies the number of fragments. You can use this special variable on many of the different instructions in OpenSCAD. And this one, where we're creating a circle, is kind of ideal. So for creating a circle, and we tell OpenSCAD how many fragments that two-dimensional circle will have, well, that equates to how many sides that circle should have. And, well, we're trying to create a hexagon, so let's give it 6. All we need to do in our code is include a little $FN equals 6. Rendering that, oh, look, we got hexagons. These are beautiful hexagons, but we're not actually recreating these hex nuts. The hex nuts are right here. We need to create pockets for these hex nuts to fit inside. So rather than creating a solid, we need to create a larger solid and then extract or subtract the hex nut that we've just created from that larger solid, giving us a place to insert these metal hex nuts into. So I'm going to add 2 more lines to our code, which will create 2 more circles for now. And then I'm going to include them inside a difference scope. It looks like this. Now, all of the solids that are inside the difference scope will be subtracted from the first solid in that difference scope. But these new solids I created are roughly the same radius as the hexagons. We need to make the first solids a little bit bigger, so I'm going to define a new parameter called twallmin, which is thickness of a wall, or let's say the minimum thickness of a wall. And I'm going to pop that parameter right in the top and set it to 0.4. The reason I'm setting it to 0.4 is a limit of my 3D printer. My 3D printer can only print lines as the thinnest it can print a line is 0.4 millimeters. So that's why I define this as twallmin. So that's right. That's why I define twallmin as 0.4. Your 3D printer may be different. So choose the one that is best for your printer. Then I'm going to add that value to the radius of these 2 circles. Notice I've multiplied it by 2 because although the printer can print a single 0.4 thick line, I kind of want to give it a little bit more meat and solidity. So I'm going to double that up so the printer will print 2 lines. Now, if we render this, everything disappeared, which is not what I expected. Oh, I see the problem. This should have been 1, not 0. Rendering that, things look a little bit more like what I expected. We have our thicker wall outside, or a thicker circle outside, with the pocket in the middle, but we lost the other one, which makes sense given what difference actually does. You'll find the details of the difference command in the cheat sheet right over here under Boolean operations. And remember what I mentioned before, difference will take the first solid in its scope and subtract the remaining solids from the first. So we've created one circle here and then subtracted all of the others from that first circle. That's not exactly what we're trying to do. What we need to do is combine these first 2 circles together, and we can do that with a union scope. Now, the way this is written, the difference instruction will take the union of both of these circles. Yes, those circles are distinct solids and they won't actually be physically combined, but it will be logically combined into a solid. And then the other 2 hex pockets will be subtracted from the union of the first. Rendering that, we get exactly what we expected. 2 circles with hex pockets carved out from the middle. Now these are really beautiful, but those hex nuts will kind of slip right through. They actually don't have any sort of pocket to fit into. And we want to make sure that when we insert the hex nut, it sits snugly onto a surface. So we're going to have to cover one of those open sides of that pocket. But see, that's a challenge in the way that we've defined our code right now, because this linear extrude function applies to everything inside that scope, which means the pockets and the surrounding, material are all linearly extruded to the same height. We don't want that. We want the surrounding material to be extruded to a bigger height than the pocket that's inside. So the first thing we'll do in our code is create another scope down here called hex pocket, and I'll take this and call it the hex pocket surround. Then I'm going to move these hex pockets into that new scope that we just created and remove them from the surround scope. Finally, we have to take this difference scope and apply it across both of these linear extrudes. Now that we've done that, this union scope is no longer necessary, so we can remove it. And let's not forget, we have to make the surround a little bit thicker, so we're going to give it just a little slice of material on the end of that pocket. Now when we render this, Oh, look at that. We've covered it up and we can still kind of see those pockets on the other side. What's going on here? So this is a rendering anomaly that's actually caused by something we'll get into in a second, but there's actually two rendering anomalies here. Let's reorient the view so we're actually looking at these hex nuts head on. And here's another interesting thing going on. You see one hex nut kind of disappear behind the other. This does not look right, and it's in the way that OpenSCAD is rendering these objects. Lucky for us, there's a really easy way to fix both of them. Well, I should say there's an easy way to fix one of them. The other one is a little bit more involved, but you'll get it. In the cheat sheet, you'll notice under linear extrude, there's this value here called convexity, and it shows up elsewhere as well. Here's one other one in rotate extrude. There's another one down here in this thing called Minkowski. This convexity business is described in the other category here under render. And clicking on this gives you some information about what this convexity is. I encourage you to read it because it's quite educational, but the bottom line is that OpenSCAD is rendering these objects in an efficient way. It's basically taking some objects that are behind one another and deliberately not rendering them so as not to slow down the system or the processes. And this convexity value basically tells OpenSCAD how many of those behind objects to render. So all we really have to do is give it a value greater than 1, and it will start to render those objects that are behind. So in our code, I'm going to create another parameter, and I'm going to call it fx0, and I'm going to make it equal to 2. The default value for convexity is 1, so 2 should improve our rendering. Then we simply add it as another value with convexity equals our parameter fx0 to every single time we do a linear extrude. Now when I render this, you can see that original kind of behind object issue it goes away. Like I can see both of these objects clearly, and that white rectangle doesn't appear. But we still have this other strange anomaly to deal with, which is this kind of fuzzy business that's happening over these hex pockets. The reason that's happening is because we've asked OpenSCAD to create a solid and then subtract a hex nut out of that solid. Now, one of those sides has that extra wall thickness that we added. That's on this side. This side worked perfectly fine. But on the other side, there's a solid on the outside and a solid which is being subtracted. Those two solids share a face. And so because though that face exists in the exact same place, OpenSCAD doesn't know whether to include it or remove it. And so what we're seeing here is almost like it's indifference of, I don't know, should I keep it? Should I get rid of it? Keep it, get rid of it? We need to tell OpenSCAD whether to keep the face and get rid of the face. And an easy way to do that is to take that hex pocket and just ever so slightly bring it out a little bit. We're going to bring it out by a value, what we call epsilon. Actually, I say we. The documentation in OpenSCAD calls it epsilon, so I'm like, okay, I'll call it epsilon too. We'll create another parameter in our code called TEPS for thickness epsilon, and we'll give it a really tiny value of 0.01. I'm giving it that value because we don't need a lot for OpenSCAD to determine that one face is outside the other face, but it's got to be small enough to not make a difference in our final output. And of course, our final output is going to be a 3D printed model, and 0.01 millimeters is way too small for my 3D printer to even notice. Your 3D printer may be different, so you might want to adjust the value depending on the limits of your printer. Once we've created that parameter, we're going to translate our hex pocket by that parameter in the Z direction. You see, this translate includes 3 components. Unlike before, we were just doing X and Y. Now this object is in 3D space, so we're going to include the Z direction. Now, just for completion's sakes, I'm going to make sure that the thickness of that hex pocket remains the same. I know, I just said it doesn't make a difference because the difference is so small, but this satisfies my OCD. Now, when you render this, that weird anomaly went away, and we can see nice, clean hex pockets. So now if you remember one of the earlier videos about limitations of 3D printing, you'll know that printing these two hex pockets face down, although possible, may cause some issues because of the bridging that's going to be necessary inside here. Although I've done it before and we can continue doing it, but this part is going to be more complex as we start adding things to it. And because I know what complexities are coming, I'm going to rotate our part such that the final output will be easier to print. Here's a through-hole version of that driver to demonstrate my thought. Right now, those hex pockets will be sitting on top over here, and it will be printed in this orientation. What I'm going to do is rotate everything so those hex pockets will be printed in this direction. Now that means a 90-degree rotation, and based on our orientation for our design, that's a 90-degree rotation around the x-axis. Back to our cheat sheet, you'll find rotate under the transformations window right over here. You'll notice that it's in here twice. We're going to use the first method. To apply this rotation, we're just going to encapsulate everything inside this rotate scope. And I've given it a 90-degree rotation around the x-axis. Once I render that, both of the hex pockets got rotated 90 degrees around the x-axis. Now to make these hex pockets a little bit easier to print, and also because I want to explore some intricacies about this rotate command, we're going to rotate these hex pockets 30 degrees such that the corner ends up at the top. Now in our code, we can do that by adding a rotation to both of these circles that create the pockets. Notice I'm rotating them 30 degrees around the z-axis. Now that's a key point because this rotation is occurring before this rotation. So the 30-degree rotation is occurring when those hex pockets are flat on the XY plane, in which case the Z-axis is straight up and down, and it'll rotate it this way. And then both of them become rotated along the X-axis to go here. If we did it the other way, where we wanted to rotate the hex pockets after the rotation, we would apply the rotation to the y-axis as opposed to the z-axis. I know it's confusing, but this is the kind of thing you're going to have to keep in mind when creating complex objects in OpenSCAD. So with this layout, when I render it, sure enough, my hex pockets are rotated the way I expected them to be. Now we always need to keep in mind the limits of our 3D printer. That's the reason we rotated it, so it will be printed easier based on things that we're going to add to this for the future. But another thing to keep in mind as well is the minimum wall thickness. You remember how we identified that it's based on the limits of my printer. We chose a value of 0.4 for that minimum wall thickness. That is based on the minimum line that the printer can draw in the XY plane. But we've rotated this now along the x-axis, so that value no longer applies because my printer has the ability to get finer detail in the z-axis. So rather than defining the parameter as a single value parameter, I'm going to change that to a three-dimensional vector, which might be the same for the x and y because my printer can only print 0.4 millimeter thick line in the X and Y plane, but because it can print a 0.16 millimeter thick line in the Z direction, I'm going to include that into this vector. So here's what that vector looks like. And then whenever we call that parameter, we need to identify which axis we're talking about. So the hex pocket surround, I'm going to use the Y thickness, which is the 0.40. And then for the radius, I'll use the X thickness. The other thing to consider when this object goes from digital to reality is that the plastic, when being extruded from our 3D printer, grows a little bit. And if we're trying to fit a metal hex nut into a pocket and we create that pocket exactly the radius of this hex nut, well, the thickness of the plastic will prevent that from actually happening. So we have to make sure that we give the hex pocket a little bit of a gap so that the actual hex nut can fit inside. Now I'm going to call that a fit gap, and just like the thickness wall or the minimum wall thickness, I'm going to define a 3D vector for our fit gap, which will allow me to adjust the value depending on which dimension we're working in. So here's the fit gap vector, and in this case I've used 0.16 for all of the dimensions, which just happens to work for my printer. And then I want to add it to all of the dimensions of this hex pocket. So the intensity gets a little bit bigger, the radius gets a little bit bigger to make sure that this thing will fit inside. Now, since our hex pocket got bigger, I need to make sure that the material surrounding the hex pocket also gets appropriately bigger. Otherwise, we're going to lose the thickness of the minimum thickness of the wall that we thought was there. Remember, we wanted to have a double wall thickness of 0.4 or 0.8 millimeters, 0.4 times 2. But if we increase the size of the pocket in the middle, then it will subtract from the wall thickness that we have, which means we won't result with the wall thickness we thought. So I need to beef up the wall by the same amount. Now, when I render it, you may have noticed it grew by just a little. By the way, you may have noticed that the circles that surround our hex pocket aren't all that circular. They have some very well-defined facets over here. Now, remember how we gave our hex pocket circles 6 sides to create hexagons, we could do the same for our exterior circles, but instead of giving them 6 sides, we can give them, I don't know, like 30 or 40 sides, which would make the circles a little bit smoother. But that's a dangerous thing to do because, as you might imagine, these circles that we're creating are quite small. And if we make the FN too high for the circles, which would give nice smooth circles, well, it won't make a difference in the end anyways, because they're too small for the printer to discern those different facets. The other challenge is when you make a lot of small fragments or segments, then that might overload the 3D printer processing and preventing it from printing the part in any case. But we want to have a lot of facets if the circles are large. So rather than using the FN, which fixes a specific value for the number of sides, we're going to use 2 other special variables called FS and FA. Going back to our cheat sheet, you'll find them in the same special variables section over here. FA is a minimum angle and FS is the minimum size. Basically what that means is FA says as the arc of the circle or whatever curved shape changes direction, the minimum angle is the minimum angle that it will allow to exist. So if you set that minimum angle really, really small, then you'll get a nice curved shape. If you set the minimum angle really large, then you'll get the facets. But of course, depending on the size of the circle, it changes. And the FS is the size of that segment, which, as you might imagine, a small segment will give a nice smooth curve, where a large segment will give a jagged curve. But that also is relevant or related to the overall size of that circle. So we're going to use both of these 2 values to determine the smoothness of our circle. All we need to do to add it to our code is include them in the hex pocket surrounds by exclusively calling them out. And I'm going to create a parameter called FA0 and a parameter called FS0. I'm going to set the minimum angle at 4 degrees and set the minimum segment size at 0.4. And when I render that, immediately my circles became a lot smoother. And here's another, by the way. You may have noticed on the right side of our window here, all these little parameters are kind of showing up. Here's the fit gap parameter, the minimum wall thickness. Look at that. We actually have the ability to control them right over here. Let's start changing some values here. Let's change the hex sync value. I'm going to move that up. And sure enough, look at the size of our solids. They're growing based on this change that I'm making to p-hexsync. And I can do the same for the intensity, which is the thickness, and watch the value or watch the thickness of these hex syncs grow. This is a neat little thing. We can do that directly in OpenSCAD without changing the code, which allows us to kind of play around with these different parameters. It's a nice little thing to have. And here we can also play with those 2 new parameters that we just created, FA0 and FS0. Watch as I increase the minimum angle. The facets around the circle change or increase to reflect that minimum angle. This is a great way to kind of play around to see which is appropriate for you. Same with the FS. If I bring that down to 0.1, you'll see my circles, well, didn't change because the minimum angle is still set at 4. I have a limiting factor here. So even though I decrease the segment size, I can't get any smaller because I've set the limiting angle. If I reduce my limiting angle or minimum angle, you'll see the circle get way smoother. You may also have noticed I can't really change the precision of any of these values. So here I'm trying to type in 4.1 or 4.2 and it won't let me do that. If I wanted to change the proportion of this hex nut, although maybe I want to have it 3.55, it won't let me get any more precise. But I can explicitly define the precision of our variables using this really neat OpenSCAD trick. By appropriately commenting the parameters like so, I'm telling OpenSCAD certain limits of those parameters. So this says it can't go any smaller than 0.1. It's going to increment by 0.02, and the maximum it can be is 20.0. The moment I render that, I now have the ability to adjust the hex sync values by the precision that I just outlined in the code. We can also do the same for values that are not vectors. So I'm going to add some limits to these scalar values down here. And when I render this, you'll see that sliders show up in the parameter window. That's fun. And sliders aren't the only thing. I can even create drop-down boxes by formatting it like this. Here I have some options for my convexity parameter. I can even organize these parameters under headings. by adding this special comment into the code, like so, all of those parameters show up under collapsible headings in the parameter listing on the right. And notice the very last parameter, I used a special header called hidden. And sure enough, it doesn't show up in this list. Whew, that was a lot. Okay, so admittedly, our model doesn't look like much yet, but we covered a lot of material and built a wonderful foundation for when we get into some of the more, I don't know, intermediate OpenSCAD 3D modeling stuff. But since we've gone through so much, we're gonna break right now and come back on the next episode where we can start taking some of those more juicy steps. So, we'll see you then.